Yeah. Okay. So I will continue. I will talk about it. Kind of rephrase the talk which I gave last year, which it was resulted in a paper with many authors. Let's see. This one, yeah, it was paper which one paper, yeah, we put on. No, it's yeah, okay, a miracle. Eigenvalues, yeah. So this one result in this paper, which I'll formulate in a second, and I will reprove and prove big generalizations of this paper. This theorem is the following: let P will be finite partially ordered set, and with n elements, and with a number of elements, and assume that it's at least 2. Then we have set of total orderings. Define the set of total orderings. So it means the set of maps from my set to usual interval with usual order, which are bijections. Yeah, so we enumerate preserving the order. Then for any two orderings, we associate a permutation which is in symmetric group. And if you have any permutation, that's not permutation by sigma, so permutation is what? It's sequence of numbers from 1 to n, yeah. And for this permutation, we associate a vector of plus minus 1s. It will be a sequence of signs. Check whether sigma 2 is bigger or less than sigma 1, sigma 3 is. Yeah, so it's in sequence of signs plus or minus to power n minus 1, because you get n minus 1 pairs. And then with any sequence of signs, we associate a variable. Just t with indices plus minus 1. So, and then we get a matrix. Matrix M filled by variables. So matrix, so indices of the matrix, it will be square matrix. Indices of M is my set of total orderings. and matrix element is T with index depend on this ratio of two order on the corresponding permutation. And what the theorem says, then all eigenvalues of this matrix are linear combinations, the linear combinations of variables. Yeah, so that's the theorem. Let me just show just one example. So we'll learn how to make the calculations. This partially ordered set is 3-element set, and this guy is bigger than this guy, and the third guy is not compatible. So what are total orderings? You should put numbers 1, 2, 3, so this guy is bigger than this guy. So there are 3 possibilities: 1, 2, 3, 1, 3, 2, and 2, 3, 1. This is bigger than this. Bigger than this, okay. There's 3 possibilities. Now we draw. Want to draw my matrix. So the matrix is labeled by this set. Three, 2, 1. Okay, now we'll have to see this permutation. So what does it mean? Well, here it will be my phi2, and here it will be phi1. So I read elements of my set in this order given by phi2 and see what's the order of phi1. I get 1, 2, 3. So 1, 2, 3. Here it will be 1, 3, 2. And here I get 2, 3, 1. Now I go to this order, so it will be 1, 3, 2, 1, 2, 3, and 2, 1, 3. And now go this order, so follows 3, 2, 1, 3, oh no, this guy, 3, 1, 2, 2, 1, 3, 1, 2, 3. Okay, so I get this matrix now. I will not draw indices anymore. Now look onto neighbors. I get plus plus, plus minus, minus plus, plus minus, plus plus, minus plus, plus minus, minus plus, plus plus. And now I just replace these guys by variables. And now I'm lazy.
Could you explain why other possibility are here?
This number should be bigger than this number. That's my order. I just replaced by inequality sign, this arrow. Yeah. Okay? And now I am lazy. I ask Mathematica what are eigenvalues of this matrix. And eigenvalues will be the following. Will be this guy, t plus plus minus t plus minus, t plus plus minus t minus plus. Yeah. Yeah, so it's very beautiful. Yeah, okay. Yeah, that's a theorem. What is nice here also, if you consider column vectors, 1, 1, 1 is eigenvector. This is, so the sum over each row is the same, which is actually was a bit surprising. So I think it's actually Schlossman and Giewiecki came to some specific class of such matrices. Then they observe that you get up to constant stochastic metric. So when Ti are positive numbers, you get Markov chain. You get Markov representation of Markov chain. And even the fact that 1, 1, 1 is common, its eigenvector is not obvious. If you look on the definition, it looks, they were kind of surprised. And then by chance, Giewiecki decided to calculate, so at least we know some eigenvalue, leading eigenvalues, what are other eigenvalues, and turns out they're really nice. Yeah, so the linear combination. And then they draw generalized to all posets. Yeah, so here what is going on? Our matrix is, of course, it's linear pencil. It's sum over variables for epsilon of these vectors. Of corresponding matrices multiplied by individual matrices consisting with zeros and 1 when these coefficients are present. Yeah, it's kind of like 0, 1 matrices. So it's kind of combinatorial object. It's a subset of squares in my table. And what we have linear combination of matrices for which we know eigenvalues. And in mathematical physics, people say that, oh, that's integrability. Then we have kind of like family of matrices because things should commute. They do not commute. This M epsilon do not commute with each other. How it's possible that you have non-commuting matrices, but eigenvalues still depend linearly? The idea is that they essentially commute. They're in certain bases, they're upper triangular, and then you don't care about things. In fact, there exists a basis. Basis in what? In algebra of functions, A will be algebra of functions. Or space of not algebra, space of functions on the set of total orderings, where my operator acts. Yeah, there is a basis such that all Mi go to upper triangular matrices. And then, if you look on eigenvalues, you just look on the diagonal part. Yeah, so it means that you get certain filtration. And in fact, filtration, so this increasing filtrations, A greater than 0, less than A greater than 1. You get some filtration on this algebra. And, sir? Yeah, but now remember it's no, it's a space of function. But first term for filtration, is the eigenvector that you know, which is 1, 1, 1. Yeah, and it's actually, I don't know, like z multiplied by identity. And it turns out there is a kind of not full flag, but sparse flag, such that filtration is strictly multiplicative. There is certain subspace containing A0 and A greater than 2, it's A greater than 1 squared. And use multiplication of functions. And A greater than 3 will be 6 multiplied 3 times, and so on. Yeah, so a less than 1 will be certain subspace of algebra functions which generates the whole algebra of functions. And degenerates means it's eventually exhausts to go to the whole space. And on associated gradient, induced operators commute. So filtration preserved by all m epsilon, induced operators commute. Yeah. Okay, yeah, so it was nice story. Yeah.
It's not the whole integer algebra preserving the flag.
Sorry?
The whole algebra preserving this flag.
Algebra, some algebra.
Sub-algebra, the algebra.
Yes, yes, yes. I'll just. Yeah. Yeah, and in fact, when we started to write the paper, we realized there is this everything. Essentially, everything was contained in some deduced very easily from some very old, sufficiently old result. It was some paper by Bidigari, yeah, somebody. This second reference, it's called something a combinatorial description. Library, and yeah, it's also many authors, also a long name, and it's generalization to hyperplane arrangements. So Duke. Okay. Yeah, it's essentially deduced from some different result. Also about it's about some class of Markov chains when you can control the spectrum. And here the situation's kind of a bit different. You automatically have Markov chains. It's not surprising result, but surprising result you can calculate further eigenvalues. And our result is very easy, just one step caller of their result. But their matrices are not so nice. We have nice matrices, but not clear where it's Markov chain, and they have Markov chain, but literally Markov chains, but not so nice matrices. And so they have this. There is actually some science, and there's a huge class of Markov chains when they discovered, and in fact they told us something like 4 different groups discovered at that time that eigenvalues are nice, and they found kind of like final ultimate generalization to hyperplane arrangements. But still I'm giving talk today, and why? Because in our we were completely ignorant. We didn't know this paper, and we have a different arguments which is much more general. So even hyperplane arrangements, it's not the ultimate generality, and kind of our K argument is more general, and I will go beyond what they proposed, and also which generalizes our result. And what is this? So now it's completely general mechanisms producing Markov chains with a controlled spectrum. The idea is the following. Suppose you have some set which is finite product of two element sets. Yeah, so it's like n-dimensional cube, vertices of n-dimensional cube. Yeah, so this symmetry of the structure is series Bn. It's kind of like get symmetric group of n elements, semi-direct product of z-mod 2 to power n. You can permute coordinates and also change orientation of coordinates. So I get this cube, and it's two element set, yeah? Then on this set, there is action of some monoid. Which I denote by y, which will have 3 to n elements. In fact, one can extend to some slightly larger monoid, which will have 4 to power n elements. What is it? Maybe I'll say first what is a larger monoid. You consider maps from xi to itself, take product from I. Yeah. You can see the self maps which are just given on maps from two element sets to itself. There are 4 such maps. It will give big guy, and it contains part you consider idempotent maps from xi to xi. Okay, if you have two element set, there is identity map. Then you can map, get two element set A, B. Then you can map A to A, B to B. Or you can map A to A, B to A to B, B to B. It will be part of these maps which are idempotent. And their compositions belong to this. And also you can swap, yeah, swap. A goes to B, B goes to A. And that will be all 4 maps. It doesn't matter which I choose, but in practice, this smallest thing is sufficient. Yeah. Yes. Yeah, so you have monoid acting, monoid say y, acting on set x, yeah? Finite monoid acting on finite set. So for each element of y, elements of y, actually I prefer not this big guy, just this retractions correspond to 3 non-empty subsets of 2 element sets, yeah? Yeah. Y can be identified with faces of n-dimensional cube. In each coordinate, you say it's you're on the left, on the right, or everywhere. Y is the faces of cube. And how one can see these operations? If you have a face of a cube, you have natural retraction of the cube to the face. Each point of y can gives kind of retraction. Yeah, so now maybe I'll try to see y is set of faces and it's a retraction, Ry.
This you mean any dimension?
Cube of any dimension, yeah. Retraction. Now, the idea is the following. Let's consider algebra of functions. Let's for simplicity, real valid functions. Functions on the set X, yeah. Yeah, in fact, how to see it? If my cube is, if my X is a set of plus minus one element, of course it's a quotient of algebra of polynomials. By ideal, xi generated by equation xi squared equal to 1. And then you have a filtration. You can restrict polynomials of degree 1, 0, 1, 2, 3. You get degree filtration. You can see the polynomials of degree less than I. And the filtration is very easy to see in the following way. What is the basis of this algebra is product monomials without squares, yeah, because square can replace by 1. And degree of polynomial and the filtration is given by the length of this product. And it gives degree filtration is obvious in this basis. And now that's kind of the claim each operator Ry star, because I have a map from set to itself, it reduces pull back on functions. It reduces pull back on functions, and it's the whole thing is tensor product. And in the case of two-element set, pullback of function 1 is always 1. So in this one-dimensional case, it's 1 goes to 1, and x goes to something times x plus something 1, and so it preserves this filtration. And if you look, it's immediate that all the operators, if you consider each base element, so it goes 1 to 1, and xi goes to axi plus b, some linear combination. Yeah, and it's immediate that it's preserved. That each element of this basis goes either to itself or simpler elements when replace one variable by 1. So the filtration is preserved by action of operators. Why the commute on associated gradient? Yeah, so it's essentially, if you consider one-dimensional space, you embed your algebra, group ring of humanoid, you identify with upper triangle matrices, and obviously things commute on the quotient. So when consider associated gradient ring, you get a different algebra by relation x squared equal to 0. It will be associated gradient ring with respect to this filtration, some sig point. And on this associated gradient ring acts, let's say, group z 2 to power n. Yeah, maybe I can add to my monoid also the force operations swapping, and which will not change. You get commutative group acting by xi goes to minus xi, and my algebra on associated gradient ring will go through this commutative quotient, and then it will commute. Yeah, so that's it. Yeah, okay. So that's very stupid source of operators from which you can calculate things. And now what's going on? We choose arbitrary numbers ty for y and y. Get 3 to power capital N numbers. If you want stochastic matrix, you want maybe put this weight 1. And then you get sum over ti ry star will be stochastic matrix with controlled spectrum, with known spectrum. And actually, what is a random walk? You just, so this thing, it means it will be probabilities. It will be probability distributions, yeah? Okay. Get probability distributions. And you jump from vertices of a high-dimensional cube. You with probability ty apply retraction ry and jump to the next element. Yeah, so that's all kind of crystal clear situation where you get this control spectrum. And when so now the following thing: if you have Markov chains and some probability size 0, then you can have kind of like subchains. There's some subsets you cannot escape. And in fact, we can do the following: consider any subset, I know, x tilde in X, any subset of vertices, and define y tilde as a set of y such that retraction of y restrict subset to maps to itself. Let me draw some little picture. Yeah, so consider like 3-dimensional cube. Yeah, in this cube I put some maybe it will be my x tilde. It will be five vertices like this, and which retractions to which faces preserve these 5 vertices. Of course, and y will be first it will be all 5 vertices, because if you have vertex, then retraction, everything retracts to this vertex. Yeah, it definitely preserves this at x. But also we can retract to some edges, and edges I see 5 edges to which I can retract. And also I see faces. Faces to which I retract, I see maybe 3. I have this guy, and also horizontal one on the bottom. I can retract here, but cannot retract up because this guy will go outside of my face. Yeah, so it's kind of very rich combinatorics. You have different subsets of a cube. You have different monoids. And then if you restrict your Markov chain, you can you use only y in this y tilde, and then it can stay only in this x tilde. You get much smaller Markov chain, but it will be part of the spectrum. You can calculate spectrum of this any smaller Markov chain. Yeah, so this is a huge source of Markov chains with spectra. With some given spectra. Okay. And yeah, so now there is a word about arrangements, yeah, hyperplane arrangements. Yeah, so I finished with this super general argument. And now go what these people done. Suppose have central hyperplane arrangement. It means that central, it means that hyperplane is passing through 0. Just to distinguish from affine, you get some, I don't know, some kind of like some plane. I don't know how to draw it. Central hyperplane arrangement. Then, too bad I removed my set. Yeah. So what will be the set x tilde? X tilde will be set of chambers. So it's connected components of my, I don't know, some vector space minus union of hyperplanes. Yeah. Pieces on which there are the chambers. Now, how we map it to what are two element sets? Indices of two element sets will be a set of hyperplanes in the arrangement. And set xi is the following. For each hyperplane, we get one side and another side. It will be space of kind of half spaces. Two half spaces. I is a hyperplane. And then each chamber sits on one part of the half space, so you get automatically x tilde is included to product of the xi. And included because two different chambers are separated by at least one hyperplane. It's really, yeah, so you get subset of a cube, some abstract story. And what will be the set y tilde in this case? Or at least some part of y tilde. It will be all possible phases of this decomposition which we have. All phases of decomposition. And this monoid, actually, people study it. It's called its phase monoid. It's phase in different sense. Yeah, so it's not about this high-dimensional cube. It gets phase monoid. And
So the faces are just subsets of I.
Faces are no. It's you have kind of decomposition on. Yeah, for example, if you have like this, you get certain faces. You get point, ray, angle, get certain faces here. Oh. It's not exactly cell decomposition because it's not compactive, but maybe at one point compactification. You get compact. So you get phase monoid, and yeah, already here is this little generalization. Instead of x, I make consider not all chambers, but chambers in any convex cone. A smaller set. And this they didn't consider, but it's very chambers in a convex cone. And y tilde one replaced by faces in this cone. In some convex cone with boundaries, some of hyperplanes. And then it's more convenient because then I don't see this high space. Like, for example, I have three-dimensional picture, but I have a cone, I can intersect with the plane. Now I can draw picture on the plane. So what I do arbitrary example. I do arbitrary convex polygon. Yeah, it will be in three-dimensional space. But if I have a cone, I can cut cone by draw picture on a affine plane, which is more convenient. So I have a polygon, and now draw some whatever, cut by some lines by some pieces. So my my set X tilde will be just domains in this thing. Now, what is the retraction? Yeah, if you have, for example, had a vertex.
So the cone has origin 0.
Yes, yes, but I tell you, I cut, I have convex cone, I make a fine picture, yeah. Yeah. So it's more convenient. I don't know how to draw three-dimensional picture literally on a blackboard, but two-dimensional is easier, yeah.
You put the the origin outside of the plane.
Yeah, consider, yeah. And in this case, we'll get a cone, yeah. So it will be easier to, yeah. Yeah, for example, if it is a point, it will be the following. If I get any other chamber, I can go try to walk to this point and approach through some nearby chamber. So it means that I here go like this. Everything here collapses to this guy. Everything here collapses to this guy, and so on. Maybe I just draw more detailed picture. Yeah, just I can make it as okay, whatever, yeah. I take, for example, this point, yeah. Maybe just okay, okay, whatever. I take, for example, this point. I claim that I collapse the whole story, the set of all chambers to these chambers adjacent to this point.
And collapse it is the same, but if I mean take DE to DE minus 1.
What does it mean? It means that for each chamber I associate some chamber attached to this guy. How do? For example, in this sector, all chambers in this sector will map to this guy. All chambers in this sector map to this guy. And the same goes to, if you get interval, just divide by 2/2 and, yeah, so it goes to things of any dimensions. And that's exactly this retraction in this high dimensional cube will be this retract, so everything will be fine. Yeah, so that was the construction. But here, little generalization can go to any convex subset instead of going to the whole sphere, which is more convenient. And the story is the following. This algebra of functions actually it has some name. It's algebra function on the set of chambers. It has a name. You know what's the name? Gelfand-Warchenko algebra. Okay. I didn't know, but okay. Yeah, so I learned a lot of things, yeah. It's called Gelfand algebra, and this degree filtration. Yeah, so it's everything that was kind of known. Yeah. Yeah. But the trouble, it's different. Oh, sorry, I have to finish. Yeah. The trouble is we get different matrices. We get matrices which make linear combinations. We get automatically 1, 1, 1 will be eigenvector. We get automatically stochastic matrices, but they are different matrices. And how to go from one to another? So is the following. Now assume that all chambers in my cone, in the cone, convex cone, which we are considering things in the convex cone, are simplicial. Now, for example, you can take the following things. You can take like affine yeah, you can take like a fine Coxeter group, and you take as your domain, get some kind of like convex 6 gone, yeah? Or you can go maybe at a little guy, other guys. Yeah, so it's some special, very special things when you get simplicial decompositions. And there are plenty of such guys, what you do, you consider hyperbolic Coxeter group, any Coxeter group, any infinite Coxeter group. And Coxeter group still acts by some matrices -1 and get something like 2 cosine pi over mij. Then as you get some matrices like this. You can realize Coxeter group by such matrices. Mij are arbitrary numbers. And this Coxeter group acts on the vector space, and it has a chamber, positive octant, and again reflection, and so the union will be convex cone, maybe infinite, not close. But then it can take any finite collection, take convex hull, and finite collections. It's easy to prove. You get finite number of things, and yeah, you can do like Escher pictures in hyperbolic plane, and there are plenty of such things. And I claim in all such situations, when things are simplicial, one can make our matrices. Our matrices will be linear combination of their matrices. And the reason is the following. When let's go again to the plane picture. If I get this simplicial decomposition, then automatically faces of the simplices, a color faces of my simplices from numbers 1, 2, up to dimension plus dimension after rank, yeah, for some simplex, then start to reflect it. And then it automatically color all walls of all chambers. So all walls of all chambers will be colored in such a way that for each chamber everything is colored in a different way. Now let's consider matrix coefficient of matrices which so we get matrices retraction to some sigma. Sigma is any stratum. For any stratum, like vertex, edge, triangle, we get retraction R sigma. And it has some matrix coefficients, like phi1 goes to phi2 and some, well, it's some 0 by 1 matrix, 0, 1 matrix. So we get huge amount of matrices. But now we can organize as a group, because we can get a face, any face, it gives certain subset of set of indices. It's like here it will be of type 2, 3, here it will be of type 1, 3, here it will be of type 2. Each face, each stratum, it has a type of the stratum, which is a subset of whatever. A subset of indices.
Excuse me, what's the type of the origin?
2, 3, because we got, yeah. So you get things of different types, and now what we can do, we can make a sum over, we consider R kind of epsilon of kind of vector, depending subset on set of indexes. This will be sum over R sigma star. It's sectional electron functions for sigma. Type of sigma is given epsilon, which is kind of plus minus to whatever number of dimensions of my ambient space. Number of colors, yeah. So I get these guys, and this again will be 0, 1 matrices. I'll finish in just maybe 2 minutes. Yeah, you have again 0, 1 matrices, and what they count. Yeah, for example, if you have if you get like chamber 2, or what's called phi 2, this ordering phi 2, and you get phi 1, what you do, you consider all depending the elements will be 0 and 1 depending on the various situations whether your phi1 belongs to this corner, when one belongs to this half space, to another half space. It's depending on you get various situations, but matrices with kind of overlap will all have one on diagonal. Our matrices have completely disjoint. You decompose in disjoint pieces, and then use inclusion-exclusion formula. Yeah, so that's the story, and here one can go to many more things. You can go beyond Coxeter groups. Yeah, just use this little picture. It definitely doesn't come from convex group because you cannot make reflection respect to this plane. You have different degrees here. Or I can do some, I made this kind of complicated picture, just maybe show something. What I do, I've done a situation that can be realized at all by lines. The only thing is you need is combinatorics. For example, I take Pappos theorem. But suppose I kind of, see, it was a bit unaccurate. These 3 points do not lie on the line. And I draw it a little bit, and then I add a little three more lines, and then cut by triangles, and get situation which is beyond hyperplane arrangement, but with the same nice properties. Thank you. Okay, so there
is a time for a few questions.
In which context is built on Varchenko algebraic here?
It's some Matroid games, I don't know, yeah. Yeah, it's combinatorics of hyperplane arrangements, maybe. Hypergeometric functions, I don't know.
But does it work for pseudo-hyperplane arrangements?
Yes, yeah, I can do two things which do not really geometric at all, yeah, but yeah.
Where are the partial orders included?
When you get partial order, it's a convex con for usual Coxeter for AN series. Partial orders have the same, and these chambers will be things in this special cone, yeah.
So this chambers, this polytope that you described, the hyperplanes which are perpendicular to that would define it. Are they perpendicular to the roots of AN, like EI minus j? For example?
Yes, exactly. Usual hyperplane arrangement.
So this is called, I think, an alcove polytope.
Yes, there's a huge literature. Yeah, one can spend whole life studying this literature. Yes, definitely. Yeah. Yeah.
Any other question?
But for pseudo-line you don't have convexity, so only you need with this star.
No. What convexity I need? It's that's again you can go to near. You have shortest path. Notion of the shortest path connected one chamber to another. That's it. Very little, yeah. In two variables, you need kind of like fake lines, such that any two lines intersect at most 1 point in this convex domain.
So, if there are no other questions, we thank the speaker and the participants of the discussion.
Okay, thank you.